And that would be, what is the equation of state? So for the equation of state, what we want to do is we want to expand the log, and we just use our favorite log expansion formula, which is this, right? Then our free energy will be the free energy of the ideal gas minus kBT by 2Vn squared integral over d cubed r f of r. Okay. So now the thing is that you can now show that if your potential is repulsive, then this integral, okay, so from here, let's go to the equation for pressure, because that's what we want for finding out the equation of state. So this is the free energy, and then we're going to have kBn of T over V. This is the ideal gas term, and then we're going to have kBT over 2, and then n squared V squared times this integral. Okay. Now we can show that if your potential is repulsive, then this integral will be negative, and therefore your pressure will increase. Wherever if your integral is if your interaction is attractive, then the pressure would decrease. So, but of course, you know, in our case, it's neither attractive nor repulsive. You know, it's attractive at longer range, repulsive at shorter range. So then what we can do the Lennard-Jones, we can plug in the Lennard-Jones potential here and do the integral. But there's a further, approximation we can make, and the approximation is that in the Lennard-Jones, we have e to the power minus beta, and now the attractive part is going to have minus u naught r over r6. Sorry, this is r over r6, and this is going to be r naught r6, and that thing is going to be e to the power plus beta u naught r naught 6 r6. And then if I look at the Meyer f function, we can expand this as beta u r naught by r to the power 6 minus 1. So that's an equality. And then I can just keep the first order term. If I keep the first order term, this one will, the one from the expansion of the exponential will cancel this exponential, and then we'll have beta u naught r naught 6 by r6. And you can do that integral. So now you can do this integrals very easily, and the details will be provided in the lecture notes. And what you'll get is, you'll get a gas law which is of this form. Where A is a constant, which will be 2 pi r naught cubed u naught by 3, and B is 2 pi r naught cubed by 3. And this gas law, just by doing a little bit of manipulation, if you multiply by just rewrite this such that kBT just becomes P plus n squared by V squared A times N by V minus B. And this is the more familiar form of the gas law known as van der Waals gas law. Now, if I go back,
I think it might be V by N minus B.
yeah, you're right. Yeah.
Yeah, I was gonna say that.
Yeah. Otherwise, it doesn't make sense. Yeah. So now we can rewrite the pressure in a form where it's N of kBT by V minus Bn minus A N squared by V squared. Okay. So we see that A has U naught. So A encodes the attractive part of the it encodes the attractive part of the interaction, and it tends to decrease the pressure. It brings the molecules closer together. Whereas B encodes just the R naught. Where's B? And what B does is that it encodes the repulsive core of the gas. And from here, because they're N gas molecules, we see that it decreases the volume, right? Because if each gas now has a little bit of a core of the size of, given by this volume, then the overall volume, free volume, is reduced by B times N. So these are the interpretation of the constants A and B. Okay? So this concludes, our, and this factor comes from the fact that there are N pairs of interaction. So this concludes our discussion on the van der Waals gas law and how you can derive it from an expansion in terms of N over V. Okay, any questions? Sorry, I ran over the time a little bit.